Hey y'all. In the next 20 minutes, we're going to talk about distributions and how they can help speed along your analysis. So, starting off with something super simple, let's say we took a survey of graduating seniors. Specifically, we asked them how old they were. So, we have 17 years old, 18 years old, 19 years old, and a couple of half ages in between. And on the y axis, we're going to count how many students per age group. And we plotted it like this. You can immediately gather some insight because your brain is so good at deconstructing images. For instance, the mode is going to be 90. You know that the average number of students per age group falls right around here. It's a fairly flat distribution, so maybe about 80 kids per age group. The average age of a graduating student falls right around here, maybe 17.75 or so years old. And these sort of insights, these snap judgments that are fairly accurate and that you can make if you know the distribution, are not specific to flat distributions. If you have something a little more complicated, but it follows a couple of rules, you can make those same sort of judgments. For example, say instead of age, we looked at the weight of each student. A lot more groups in the first place because students' weights vary from this to that, everything in between, and a lot more variability within those groups. This sort of distribution with this sort of shape that's symmetrical across the mean is called a normal distribution or a Gaussian distribution. And it's really common. It's going to come up in a lot of fields, and it has some specific characteristics that we can leverage. For example, the mean, median, and mode of a Gaussian distribution are all exactly the same. So here's our mean. It also happens to be the mode. You can see that this group has the highest number of students in it. And it's also the median. Also, for a Gaussian distribution, 95% of your data is going to fall within 2 standard deviations of the mean. And 68% of it will fall within 1 standard deviation of the mean. So there's a couple of terms. If you don't know those, we're going to explain very quickly. Here's how you calculate the mean. A lot of people think average. They're not exactly the same thing, and there are actually many kinds of averages. But when you're calculating the mean, n is the number of instances that you have, and x sub I are the specific instance values. So say you have 3 pumpkins, 5, 6.5, and 5.3 pounds. You have 3 instances of values, so your n is 3, and the x sub i's are going to be 5, 6.5, and 5.3. So you sum those, divide by your n, and you'll get 5.6, and that's the mean of the weights of your pumpkin. Now, much less recognized is variance or standard deviation. They're not the same thing. I didn't mean to make it sound like they were. Your variance is denoted s squared and is calculated like so, and your standard deviation is the square root of that, or just s, often denoted sigma. And a lot of metrics are calculated in standard deviations. That's why it's good to be familiar with it. And a great way to illustrate what standard deviation is with a short visual. Here's a normal Gaussian distribution. There's your mean, x. So 1 standard deviation, that is 1 sigma, is going to encompass all of this. It's going to be plus or minus 1 standard deviation, and it's going to cover 68% of your data. Okay? If I go out 2 standard deviations, then I can actually grab all of this too. And that accounts in total for about 95% of the data. So standard deviation is sort of how far from your central cluster is a lot of your data. And the reason that's so important is because instead of, say, giving you a bunch of data like that, or a bunch of flat files that you have to process somehow to get into a usable format, I can just tell you, hey, this distribution is normal, it's Gaussian, It has a mean of 160 and it has a standard deviation of 32. And from that information, you could recreate a sample data set that you can work with. And a lot of ready-made plug-and-play tools are going to work perfectly with this because you're assuming normal distribution. And that's going to speed your analysis up a lot. So if you can approximate your data set with a known distribution model, it's going to save you a ton of time and a ton of work. Now, there are lots of other distributions. There's log normal and exponential, and we'll get to those. And they can also be summarized with a couple of parameters. So it's important to recognize the different sorts and sort of always have them in your back pocket. Last thing before we do some exercises, sometimes we want to compare two distributions, and the best way to do that is not necessarily with Cohen's effect size, but this is a simple way to do it. So Cohen effect size measures the sort of difference in means between two groups. Say you wanted to compare the grades of physics students and chemistry students. It's difficult to do that accurately because there are different circumstances governing each of those data sets. The professors are different, they grade differently, the material is different. But this is sort of a way to see the difference in the two. So the difference in means divided by the average of the standard deviations. And this is what that looks like. You have two distributions and then the difference between them. Though this visual is a little misleading because it doesn't take into account this denominator term. But this is sort of a way to visualize it. It kind of tells you the difference in the means in a more accurate way while accounting for the standard deviation. That is, while accounting for all of the weird data over here that isn't necessarily clustered right around the mean. So it's one way to compare things. It's not the best, but it's fast and it's fairly handy in a lot of cases. So with that out of the way, we can do some Jupyter exercises. So we're going to hop on to the computer now. We're not going to be using ThinkPlot, which is the library written by the text author, because it's too narrow in scope. Instead, we're just going to learn how to use matplotlib and Seaborn, which are standard Python libraries for plotting, and it's going to be much more beneficial in the long run if you're familiar with these. So go ahead and add these two lines to that first cell, matplotlib.pyplot, and we're going to alias it as PLT, and Seaborn, which is aliased as SNS. And we will use both, but we're barely going to touch the capability of either because there's just so much there. The rest of these cells, really basic stuff, we're going to skip over a lot of it. It's important to note that we are loading a few data frames, well, 4 data frames. Preg, consisting of all the pregnancy data. Live, consisting of a subset of preg, specifically live births, hence the name. And 2 more firsts, which is a subset of live, specifically only the firstborn children. And others, which is also a subset of live, but the second, third, fourth, and so on born children. That is not the firstborn children. Okay? Here is a Cohen effect size implementation. We learned about that in the first part of the video. We can go ahead and read through that, or we can just go ahead and implement it because we talked about it already. Compute the Cohen effect size to quantify the difference between the groups being firstborn babies and other babies, specifically the total weight of each. So Cohen effect size, and then we're going to feed to that function the 2 groups. First dot total weight pounds, and our second group is others dot total weight in pounds. Shift enter. So remember, Cohen effect size is calculated in standard deviations. So about 1/10 of a standard deviation, and I don't know what the standard deviation is. It's measured in pounds in this case, and I don't know if that's significant because I'm not an expert in newborn demographics. But you can see How if you were, that you might be able to draw some insight from a comparison like this. Maybe firstborns really are heavier or lighter. In this case, I assume it would mean that they are, let's see, calculated one minus the other, so one minus the other, which means that the others are heavier because it's a negative number. Okay, so make a histogram of the total income of the respondent's family. Okay, so to use Seaborn to plot, this is what we do. Set up an axis object, we'll call it AX1. Seaborn, which is aliased as SNS, dot, and this is the function, distribution plot. Okay, and to this we pass our data. Super easy. Resp, that's our data frame by name, dot, our column by name, total income for the respondent. Now we're going to set the X label. We'll call it total income for the respondent. And Y label we'll call count. And finally call PLT, that's matplotlib, aliased as PLT, dot, the function show to show our plot. Shift enter. So you'll notice it looks funny. There's a weird line here, and these aren't integer numbers. These aren't the counts. This is some weird decimal system. We're going to learn about that, but for now, just know that it's called the kernel density estimation, and we're going to turn it off. So pass this parameter, shift enter again, and there's what we want. You can see that it's fairly flat, kind of tails off towards here. So 1, 2, 3, so on are the lowest income brackets. We know that because we read the chapter and we understand our data. And the highest income bracket is 14. And 14 also holds the highest number of mothers, so about twice as many as any other, and about 3 times as many as the lowest income brackets. So maybe that answers questions that you have. Maybe it sparks curiosity as to why this is the case. It might be the beginning of several more questions that lead you to more thorough analysis. But right now we're just looking at distributions and how to do this in the notebook. Make a histogram of AJAR. So same thing. We'll call this one AX2. That access object is created by calling the library seaborn.distribution plot, passing the data, in this case resp.AJAR is a specific column. We're going to turn off kernel density estimation, AX2.set to make our labels. So the X label is actually going to be age.r, so here's a shortcut. You don't need to make it, so just pass the Y label and plt.show to create it. You can see lots of peaks and valleys, but fairly flat across the peaks and fairly flat across the valleys. I don't know why that might be the case. It probably has something to do with rounding, right? Imagine that most mothers don't say that they're, this is 20, 21, 22, 23. Yeah, so there's some rounding. These actually aren't divided into equal intervals. So, that's interesting. Okay. Make a histogram of the number of family members in the household. It's the same process. Make a new axis object called AX3 or whatever you want. Go ahead and do that. Make a histogram of parity. Same thing. I wouldn't do this. Hist and largest both belong to ThinkStats, and we don't want to become experts in the ThinkStats2 library because it's, like I said, too narrow in scope. Let's investigate whether people with higher income have higher parity. Okay. So select the highest income respondents and plot their parity. Okay. So let's call this group rich, and rich is going to consist of the respondents, specifically the respondents where total income for the respondents is the highest that there is, the 14th bracket. Okay, let's set up AX3 dot distribution plot, and rich, we're plotting the parity, and turn kernel density estimation off. AX3 dot set, we're going to set our Y label to the same thing, count. PLT dot show. Data frame object has no there's a typo right there. Total income. Shift enter, there it is. So if I understand parity correct, this is the first child for about 500 women within this highest income bracket. The second for about 220, 230 women. The third for almost 300 women, and it trickles down from there. So that's not too surprising. I'm not sure that there's a lot of insight to be had there. I bet it's actually pretty similar to all other income brackets. Find the largest parities for high income respondents. That's a bit like finding the value counts and then finding the highest within that set. So we did a bit of that in chapter 1. Compare the mean of the high income respondents. So here you compare the mean, and here you recompare the two groups, but this time using Cohen effect size, which should yield a more accurate comparison, a more accurate description of the difference. So we won't do that in its entirety, but I will walk you through not creating the rest of the groups. So the respondent, specifically the respondents where the income, total income for the respondent is less than 14. Okay. And now not rich is everyone else that's not included in rich. So that is everyone in income brackets 1 through 13. So the last few exercises of chapter 2 ask us to define 3 functions. Mode, to compute the mode of a distribution. All modes, which returns all the modes of that distribution. And weight difference, which explores the difference in birth weights of firstborns and not firstborns. None of these are very difficult. The skeleton is written for us, and the answers are in the same code repository. So you can see how simple they are. It's just sort of iterating, sorting, and returning portions of that sort. And the last bit is just sort of implementing Cohen effect size and making sure your variables are calculated correctly. So it's good practice if you are not very familiar with Python and you want a little more hands-on script writing. Otherwise, it's not worth a ton of time. That's it for chapter 2. Chapter 3 is probability density functions, I believe, or maybe probability mass functions. So we'll get started with that. It's a little more difficult, so if you want to follow along hands-on, be sure to watch the setup video that teaches you how to get this environment up and running, as well as downloading the correct code repository.